we'll prove one more property of the center of mass. Okay, that is if there are two particles, R1 and R2, at radial distance R1 and R2, okay, and this is the line joining these two particles. We know the center of mass will lie somewhere in between, depending upon what are the masses of these two bodies. So let this be M1, let this be M2, and this is our center of mass. Okay, here. So from center of mass, let this distance from here till the first body, let this distance be R1 prime. Okay. And the distance from the center of mass to the second body, let this be R2 prime. So what we need to prove is, this is called the collinear property, that the center of mass of such a system will always lie on the line joining the two bodies. Okay, that is, this is the line, straight line joining these two bodies. The center of mass of such a system will always lie somewhere on the line joining the two bodies. We intuitively have already discussed that it is the case like that. If this is heavier, the center of mass lies towards here. If this is heavier, the center of mass will lie towards here. But we need to mathematically, rigorously prove that even though it lies here or here, it doesn't matter. But what we need to prove is that it will always lie on this line joining these two particles, okay? No matter what these masses are. If this is very heavier, it will lie here. Slightly heavier, it will lie here. But always on the line joining the two bodies. So this is called the collinear property. So mathematically, if we need to prove that, what we need to prove is that R1 prime plus lambda times R2 prime is 0. Okay? Why? Because if this is particle 1, this is particle 2, this is a line joining the two particles, and this is the center of mass. Okay? And this is R1 prime. This is R2 prime. Now, if the center of mass lies at the line joining the two particles or the two bodies, then what we'll have is, if this is R1, and if we add lambda times R2 to R1, we can always get it to be 0. Okay? For example, just imagine that the center of mass lies at the midpoint. Then R1 and R2 are the same. If R1 and R2 are same, so this will R1 prime and R2 prime are same. So this will be nothing but, we can choose lambda to be 1, and we'll have R1 prime plus R2 prime is 0. Okay? But if the center of mass didn't lie at the center of the line joining these two particles, and it supposedly say it lies somewhere above this line, okay? Somewhere above this line. And this was our R1 prime, and this was our R2 prime. So if the vector is, if these two vectors were at an angle, R1 prime and R2 prime, and if you add these two vectors, no matter whatever you multiply with R2 prime, if you add R1 prime plus R2 prime, you can very easily see that they can never cancel each other because the directions of these vectors are different. Okay? No matter what you add to R1 prime, if the direction is this, and if you add to R1 prime lambda times R2 prime, so if you try to change the direction of this vector by multiplying it lambda, making it smaller or making it larger, but it can never be equal to 0 because the direction of these vectors are different. Only when the center of mass lies at the line joining these two particles will this R1 prime and R2 prime lie in a straight line, and then we can get and then if we add them, we can get them to be 0. Okay? And why the lambda factor exactly? So many of you would have already guessed it, but still, the factor of lambda is just to account for the fact that the center of mass can lie anywhere on the point. For example, if this was a line joining the two particles, this was M1 and M2, and we need to prove that, what we have is, if M1 is very, very greater than M2, as we discussed, the center of mass will lie somewhere over here. So we see that R1 prime will be very smaller than R2 prime. Okay. But if we use this thing, if we see this expression, not accounting for this equation, just this expression, what we see is, even though R1 prime is smaller than R2 prime, but because these vectors lie in the same line, we can always multiply R2 prime with a constant to reduce the length of the R2 prime. So R2 prime right now is this, but then we can multiply it, say, by 0.1, such that the length of the vector reduces. And once it reduces to the same length as R1 prime, when we subtract them, they will turn out to be 0. Okay? That's why we take into account the lambda factor, such that even if the masses are disproportionate, but the center of mass is lying at the line joining these two bodies, which we need to prove, we can always check that if this was larger, we reduce it by a certain length, and then we subtract them. But this case would not have worked had the center of mass would have not lied on the line joining those two particles. Because if this was the line joining these two particles, M1 and M2, and the center of mass was here, same case that M1 is heavier than M2, so R1 prime would have been this, R2 prime would have been this. Now, even if you try to reduce the length of R2 prime, because they are in different directions, they can never cancel each other. Okay? So this expression, what it proves is, if this is equals to 0, if R1 prime plus lambda R2 prime equals to 0, then the center of mass is lying at the line joining these two particles. And if this is not equal to 0, which means the center of mass is not lying at the line joining these two particles, it is lying somewhere above or somewhere below. And it is not turning out to be 0 because the directions of R1 prime and R2 prime are different. All right? So we need to prove this thing now. Okay. So what we do is, so this was our diagram. So what we do is, since we'll be needing this diagram, so I'll start with the equation with here itself. So we start with a basic expression that our center of mass equals M1 R1 plus M2 R2 divided by M1 plus M2. Okay. Now, if you see this triangle over here, this is our center of mass, this is R1 prime, and this is R1. So R1 prime plus our center of mass equals R1. Okay, using these three vectors. Similarly, if you see this vector over here, we'll have our center of mass plus R2 prime is R2 vector. Okay, so we'll just write down these expressions. All right. So what we have is R1 prime is R1 minus our center of mass. Let this be 1, let this be 2, using 1. Okay. So now our center of mass is nothing but Okay. Now we take the division on both sides of the term. So we'll have m1 plus m2 r1 minus m1 r1 plus m2 r1 on m2 r2 whole divided by m1 plus m2. All right. So you open this up. So this will be m1 r1 plus m2 r1 minus m1 r1 and minus m2 r2, because this is bracket over here. When the bracket opens, there will be a negative sign over here. So this is minus m1 r1 minus m2 r2 divided by m1 plus m2. Okay. Now this is equal to, so this term and this term will get cancelled. So this will be m2 r1 minus m2 r2 upon m1 plus m2. Okay. Now we'll take m2 common here. So this will be m2 r1 minus r2 m1 plus m2. And this is nothing but r1 prime. Okay. Because we started with the expression for r1 prime. This is all our expressions for r1 prime. So this is r1 prime. Now what we do is, just to simplify our calculation, make it easier, we define a vector r such that r equals to, or let's take different notation, this r is r1 minus r2. Now r1 is the radial coordinate for the first particle, r2 is the radial coordinate for the second particle, but this r is not a radial coordinate of any of the particles. R is just the mathematical radial distance we have defined just to simplify our calculation. So we define a new abstract radial distance r, which is r1 minus r2. Okay, and we substitute it back here. So this will be nothing but m2 r upon m1 plus m2. Okay, which means r1 prime is m2r m1 plus m2. Okay. Again, to simplify, so all the simplifications we are doing, you need to also know that these simplifications are not random. These simplifications are because of some specific reasons, because we need to arrive at the result that of the collinear property, which was r1 prime plus lambda times r2 prime is 0. Okay, we need to prove that. So for proving that, we started with this expression for our center of mass. Then we found the expressions of r1 prime and r2 prime. We haven't yet found for r2 prime, we are finding for r1 prime. So for r1 prime, we went like this. Then we did the subtractions and cancellation of the term. And here we assume that r1 minus r2 is r. Okay, and we got this expression. And here what we'll assume is, we'll define a new constant. We'll define new constant mu, which is nothing but m1 m2 upon m1 plus m2. So later on, when we go further, we'll find that the nu is nothing but the reduced mass of the system. So if we have two masses m1 and m2 at a certain distance from each other, we have, one is the total mass, we define capital M, which is m1 plus m2. And second thing which we define in certain problems is the reduced mass. Reduced mass is Nothing but it is defined by like this. And if you open this up, you multiply m1, m2, take this on the other side, you'll get the expression of reduced mass to be this. Now, reduced mass is not a physical, does not have any physical significance. It is just used as an abstract concept to help us with our calculations. Okay, so many times we'll be using this concept of reduced mass. So we define nu as m1, m2, m1 plus m2. So for that, we multiply and divide by m1. So this will be m1, m2 are okay. So this will not be nothing but, so m1, m2, m1 plus m2 is mu. So this is mu r upon m1. Okay. So anytime when we have constants over here, so here we have m1, m2, and m1 and m2 are constants. So here we specifically use the concept of reduced mass, but we can always replace such expressions by any constant. Okay. Because of course the value of m2 upon m1 plus m2 is a constant. So we could have also defined this thing as r1 prime equals to, say, alpha times r. Okay, this is also perfectly acceptable. But here we are using, since we already have defined mathematical abstract quantity as reduced mass, which we use multiple times in future also. So we are, instead of taking some alpha, we are taking this constant. Okay. So we arrive at r1 prime equals to mu r upon m1. Okay. Let this be equation. Let this be equation 3. Similarly, we'll find the expression for r2 prime. So r2 prime, from the diagram, if you see, this is our center of mass. So our center of mass plus r2 prime is this vector, r2 vector. So our center of mass plus r2 prime is r2. Again, the steps will be similar. So we'll define r2 prime is r2 minus our center of mass. Again, our center of mass is nothing but m1 r1 plus m2 r2 m1 plus m2. Again, taking m1 plus m2 on both sides, we'll get okay. And if you open this up, this will be m1 r2 plus m2 r2, and this will be minus m1 r1 minus m2 r2, because we take the negative side inside after opening the bracket. And similarly as last time, what you'll find is that this m1 m2 r2 gets cancelled by m2 r2 over here. Okay, so what will be left is m1 r2 minus m1 r1. Okay, because this term, this is positive m2 r2, will get subtracted by negative of m2 r2. So we'll have m1 r1, m1 r2 minus m1 r1. So we'll have m1 r2 minus m1 r1 upon m1 plus m2. Okay, so taking m1 common here, we'll have r2 minus r1 m1 plus m2. Now, since we have already defined the abstract vector R as R1 minus R2. Okay. So R2 minus R1 will be nothing but negative of R. All right. So this will be nothing but minus M1R upon M1 plus M2. Again, since we have already defined the expression for mu, reduced mass, which was nothing but M1 M2 upon M1 plus M2. Okay. So here, just to use this expression mu, what we'll do is multiply and divide by M2. Okay. So this will be minus M2 M1 R upon M2 M1 plus M2. Okay. So M1 M2 M1 plus M2 will be nothing but the reduced mass mu, and this M2 would be left outside. So this will be nothing but minus nu M2 times R. This is equation 4. Okay. Now, what we need to prove is, which we already wrote at the initial stage, that R1 prime plus lambda times R2 prime is 0. Okay. This is the collinear property, and this will, if this is satisfied, what will be proved is that the center of mass always lies at the line joining the two particles. Okay. As we already discussed physically also why this is the case. So now if we have the equation 3, that is R1 prime is nu R by M1. Okay, so we'll write this there also. R1 prime is minus nu R by M1. This was our equation 3. Now adding 3 and 4, we get R1 prime plus R2 prime equals minus mu R by M1. Hold on. Okay, so this was positive over here. It's not negative. Yeah, this is positive over here. So this is positive nu R by M1 minus this thing over here, nu R by M2. All right. So what we have is now there are two ways. Since we needed to prove this result, what we can do is we can add these equations like this over here and proceed ahead. And what we can also do is to simplify, to reduce our steps, which we'll be using to calculate this, what we can do is take this M1 this side and take this M2 this side. Okay, and then add these equations. So then what will happen is, that is just a easier way. Otherwise, it will take few more steps. So we take M2 this side. So this equation becomes M1 R1 prime equals to nu times R. Okay, and this equation becomes M2 R2 prime equals to nu times R. Okay. Now when we add these two equations, what we get is M1 R1 prime plus M2 R2 prime equals to nu R minus nu R. This was negative over here. Okay. So you're adding this to this is M1 R1 prime plus M2 R2 prime mu times r minus nu times r, because for m1 r1 prime case we have a positive sign over here, but r2 prime case we have a negative sign over here, and this negative sign came because we had defined our abstract r vector as r1 minus r2. So when we are solving for r1 prime, we got r1 minus r2, so we replace it by r. But when we were solving for r2 prime, we had got r2 minus r1. So we had to reshuffle it, and therefore we got, so for r2 minus r1, we substituted minus r in this expression, okay? So that is why there's a negative sign over here. So we take m2 this side, m1 this side. These are the two equations. Negative sign over here. We add these two equations. So here it is nothing but mu r minus mu r. So this is nothing but 0. So we have m1 r1 prime plus m2 r2 prime equals 0. So we have m1 r1 prime plus m2 r2 prime is 0. This implies if you divide this expression by m1 on all the sides, so this will be divide by m1 on both the sides. So what you'll get is m1 upon m1 will be 1. So this is r1 prime plus m2 upon m1 r2 vector equals to 0. Okay. Since m1 and m2 are both constants, let it be defined as lambda times r2 is 0, because lambda can be any constant. Okay? So what we have done is, this is nothing but what we started to prove. This is nothing but the proof for the collinear property, because this is what we started. So in this case, this is what we needed to prove. That is the collinear property. And we discussed also, I told you why we had chosen this expression to prove the collinear property. That is, the center of mass always lies at the line joining the two particles. And for that, we need to prove mathematically that this is the case. Because if this is satisfied, that would have proven that the center of mass lies at the line joining the two particles. So we have finally proved here that this indeed is the case. Okay. So this was the last property. So we have discussed three properties as of now. First property is that if there's an extended body, we can assume that the external force which is acting on the extended body is acting on not on the extended body, but on a point inside the body, which we define as the center of mass. So the total external force acts on the center of mass. Second thing is, the center of mass, the point has a mass equivalent to the whole body. So the total mass of the body is supposed to be concentrated at that point. Okay, so that was second property. And the third property is the collinear property. That is, if we have two particles and we've calculated the center of mass, the center of mass will always lie at the line joining the two particles. Okay, so this was our collinear property. So now we have, yeah. So what we have is, now consider these two masses, m2 and m1. Now what we'll do is, we'll try to find what is the velocity of the center of mass along with the moment of the center of mass. Because till now we have just found out what is the radial position of the center of mass if we have two bodies. Okay. So the radial position of the center of mass of two bodies, which have the radial distances r1 and r2, as our center of mass is m1 r1 plus, or we'll just write the reduced expression, which would be summation m1 mi ri summation I goes from 1 to 2, because there are two particles, upon I goes to 1 to 2 summation mi. Okay. Now the velocity of center of mass is nothing but the derivative of the radial position of center of mass. Okay, V is d r center of mass by dt. So this derivative will go on both of these terms. So it will be d by dt of summation I from 1 to 2 mi upon mi. All right. So since m is constant, mi is constant, this d by dt, and this mi is also constant. This again a summation over here. Since mi and mi are constant, this d by dt will act just on this vector ri. Okay, because ri is the thing which is changing because these particles are moving. So this will go inside, and this will be nothing but summation I goes from 1 to 2 mi d ri by dt upon summation mi. Okay, so this d ri by dt is nothing but the velocity of the rth particle, rith particle. So this will be nothing but, write on your slide. Okay, so this is the expression for the velocity of the center of mass. Okay, so we now know how to calculate the center of mass, and how this is also, and we also know to calculate the velocity of the center of mass. So the moment of the center of mass, P center of mass, will be nothing but the total mass, because this is the mass of the body which is concentrated at the center of the mass, which is the total mass of the body, times the V center of mass. Since we know what is the mass of the body, and since we have the expression for the velocity of center of mass, so this is the momentum of the whole body defined at the center of mass. Okay,